When we speak of temperature, we instinctively think of matter, moving molecules, vibrating atoms, warm air, cold metal. So the phrase temperature of the sky appears meaningless at first glance. After all, the sky is mostly empty, space has almost no atoms, there is nothing to heat up. And yet, modern physics assigns a precise temperature to the sky, 2.725 Kelvin, measured with extraordinary accuracy. This immediately raises a fundamental question. How can something with almost no matter possess a temperature? In thermodynamics, temperature is not fundamentally about matter, it is about energy distribution. More precisely, temperature characterizes how energy is spread among degrees of freedom. Those degrees of freedom can belong to atoms, kinetic energy, molecules, rotational or vibrational energy, radiation, photons. This last point is crucial. Photons have no mass, but they do carry energy, and a collection of photons can have a temperature if their energies follow a specific statistical pattern. In the 19th century, physicists studying heated objects discovered something remarkable. Hot objects emit radiation. The radiation spectrum depends only on temperature, not on material, shape, or composition. This led to the concept of black body radiation. A black body is an idealized system that absorbs all incoming radiation and emits radiation with a spectrum determined solely by its temperature. Radiation itself, therefore, can be thermal. This insight allows us to define temperature without matter. When physicists say the sky has a temperature, they mean the radiation arriving from all directions in space has the spectrum of a black body at 2.7 K. This is not air temperature, this is not weather, this is not sunlight. It is a universal background glow, extremely faint, filling all of space. We call it the cosmic microwave background, CMB. The temperature of the sky was not predicted first, it was discovered accidentally. In 1965, two radio engineers at Bell Labs, Arno Penzias and Robert Wilson, were calibrating a microwave antenna. They encountered a persistent noise, present day and night, same intensity in all directions, unaffected by season or location. They tried everything, removed electronics, cleaned the antenna, even removed pigeon droppings, famously called white dielectric material. Nothing worked. The noise remained. Unknown to Penzias and Wilson, theorists had already predicted such radiation. In the early 1940s, George Gamow, Ralph Alpher, Robert Herman studied early universe thermodynamics. They reasoned the early universe was extremely hot. Matter and radiation were in thermal equilibrium. As the universe expanded, radiation would cool. That radiation should still exist today, faint and cold. Their predicted temperature a few Kelvin. Penzias and Wilson had found it. The radiation they detected had a nearly perfect blackbody spectrum, was isotropic, same in all directions, and corresponded to 3 K. This was not random noise, it was the thermal afterglow of the early universe. Penzias and Wilson received the 1978 Nobel Prize in Physics. From that moment on, the sky officially had a temperature. If the universe has been expanding and cooling for billions of years, one might expect, eventually space should reach absolute zero, 0 K. But it hasn't, and more importantly, it cannot. As space expands, wavelengths of photons stretch, energy per photon decreases, temperature drops, but photons are not destroyed. They dilute, redshift, and weaken, yet they remain. Even today, every cubic centimeter of space contains hundreds of CMB photons. They form a near-perfect thermal distribution. This makes absolute zero unreachable for the universe as a whole. Absolute zero requires no accessible energy states, no excitations, no radiation. But the universe has a history. That history left a thermal imprint, which expansion can cool but never erase. In this sense, the sky's temperature is a memory of the universe, a fossil record written in radiation. Later missions refined this picture. COBE in 1990s confirmed the black body spectrum. WMAP measured tiny temperature variations. Planck's satellite mapped the sky to micro-Kelvin precision. These experiments showed the sky is almost uniform, but not perfectly. Those tiny variations seeded galaxies. Yet even without structure, the mean temperature remains 2.725 K. One might reasonably object, how can the universe have a temperature if nothing is in thermal contact with anything else? In everyday thermodynamics, temperature arises through collisions and equilibrium between particles, but the cosmic background radiation is different. In its earliest stages, the universe was extremely hot, extremely dense, highly interactive. Photons, electrons, and baryons scattered constantly. This created a state of near-perfect thermal equilibrium, described by a Planck distribution. U of nu T equals 8 pi h nu cubed over c cubed times 1 over e h nu over kt minus 1. This equation, derived by Max Planck 1900, is one of the most precisely verified formulas in all of physics. The key insight: once a radiation field acquires a black-body spectrum, cosmic expansion preserves its shape. Expansion redshifts frequencies, but does not distort the distribution. Thus, temperature becomes a property of the entire space-time, not a local interaction. Approximately 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to form neutral hydrogen. This moment is called recombination. After this, photons stopped scattering frequently, radiation decoupled from matter, light began to travel freely. From that moment onward, the universe carried a frozen thermal signature, cooling only due to expansion. This is why the sky still has a temperature today, even though no equilibrium process is ongoing. In laboratory physics, temperature belongs to a system inside a box, but the universe has no walls, no external environment, no heat bath, yet it has a well-defined temperature. This forces a conceptual shift. Temperature can be an intrinsic property of space-time itself. This idea appears repeatedly in modern physics: Unruh temperature, Hawking radiation, de Sitter horizon temperature. The cosmic microwave background represents a maximum entropy state for radiation given the universe's expansion. As Roger Penrose emphasized, the early universe had low gravitational entropy but extremely high thermal uniformity. This combination is rare and deeply puzzling. The uniform sky temperature reflects a universe that began in an unusually ordered state, then evolved irreversibly. Thus, the sky's temperature is not just a number, it encodes the arrow of time. 5.3. Why the temperature is so uniform. Measurements show temperature variations of only delta T over T equals 10 to the minus 5. This extraordinary uniformity demands explanation. Two major ideas contribute: early thermal equilibrium and inflationary smoothing. But crucially, the sky's temperature is the most precise measurement of cosmic uniformity we possess. In quantum field theory, vacuum is not empty. Fields fluctuate even at zero temperature. During cosmic expansion, tiny quantum fluctuations were stretched, imprinted as temperature variations in the CMB. This connects quantum uncertainty to galactic structure. Few observations link quantum mechanics to cosmic scale so directly. In advanced levels, temperature is inseparable from entropy. In statistical mechanics, temperature is defined as 1 over T equals the derivative of entropy with respect to energy at constant volume. This definition does not mention matter, particles, or collisions. It tells us temperature measures how rapidly the number of accessible microstates grows with energy. The cosmic microwave background, therefore, has a temperature because it occupies a vast number of photon microstates. Those states obey Bose-Einstein statistics. Their entropy is extremely high. A surprising result from cosmology is that most of the observable universe's entropy is not in stars, black holes, or matter, but in the cosmic radiation background. This was emphasized by Charles Bennett and later by Sean Carroll. Even though the radiation is cold, its entropy is enormous because it fills all of space.
Thus, the sky's temperature is a macroscopic manifestation of entropy, not heat in the everyday sense. A deeper question arises: why does cosmic expansion preserve a thermal spectrum at all? The answer comes from Hamiltonian mechanics, not thermodynamics. Liouville's theorem states that phase space density is conserved under Hamiltonian evolution. In an expanding universe, photon momenta redshift, spatial volume expands, but the distribution function remains invariant. This means a Planck spectrum remains a Planck spectrum with a rescaled temperature. This is not accidental, it is a consequence of fundamental symplectic structure of physics. So the sky has a temperature because the universe obeys Hamiltonian dynamics even while expanding.
By standard definitions, temperature requires equilibrium, but the CMB today is not interacting, so why does temperature remain meaningful? Physicists distinguish between kinetic temperature, collisions, and effective temperature, distribution shape. The cosmic background has no collisions, no equilibration, yet an exact Planckian form. Thus, its temperature is an initial condition temperature, not a dynamically maintained one. This is conceptually similar to frozen distributions in collisionless plasmas, relic neutrino backgrounds. At this level, temperature becomes a parameter labeling a distribution, not evidence of ongoing thermal activity. This is subtle and often misunderstood even by advanced students. In flat spacetime, vacuum has zero temperature, but in curved spacetime, vacuum states are ambiguous. This leads to Unruh effect, accelerated observers see heat, Hawking radiation, black holes radiate, de Sitter temperature, expanding universes have horizons. The cosmic background temperature exists alongside these effects. This raises a profound idea. Temperature is not only a property of matter, it can be a property of horizons and spacetime geometry. Our universe is approximately de Sitter-like due to dark energy. That implies a future horizon with its own associated temperature. In the far future, the horizon temperature may dominate over the relic radiation temperature. This connects cosmic temperature to quantum gravity, not classical thermodynamics. Why 2.7 K and not something else? Physics alone cannot yet answer this. The temperature reflects initial energy density, early expansion rate, and degrees of freedom present in the primordial plasma. Physicists such as Steven Weinberg emphasized many cosmic parameters are boundary conditions, not derivable laws. The sky's temperature is one of them. At a fundamental level, temperature is not an intrinsic property of objects, but of ensembles. For the cosmic radiation field, the relevant ensemble is not canonical or microcanonical in the usual laboratory sense, but a collisionless ensemble evolving in an expanding spacetime. The phase space distribution function for photons is f of x, y, t. In an FLWR universe, this function evolves according to the collisionless Boltzmann equation. df over dt equals 0. This deceptively simple equation implies that the distribution function is conserved along geodesics. Thus, once the photon field acquires a Planckian form, it cannot lose it without interactions. Temperature becomes a label on a conserved distribution, not a thermodynamic variable tied to relaxation. The temperature of the cosmic radiation scales as T proportional to 1 over A of T, where A of T is the cosmological scale factor. This relation is not empirical, it follows directly from momentum redshift, P proportional to 1 over A, energy-temperature correspondence for massless bosons, invariance of the distribution function. This makes cosmic temperature a geometric quantity, directly tied to spacetime expansion. The sky has a temperature because the universe has a scale factor. In an ideal universe, photon number is conserved after decoupling. The Planck spectrum remains exact. However, real physics introduces subtleties. Processes such as double Compton scattering, Bromstroming can create or destroy photons at very early times. These processes determine how perfect the blackbody spectrum is and when deviations can survive.
The absence of observed spectral distortions places strong constraints on early universe energy injection, exotic particle decay, and primordial turbulence. Thus, the sky's temperature encodes negative information, evidence of what did not happen.
A deeper interpretation involves quantum entanglement. The early universe was a strongly coupled quantum system. Photons today may be weakly interacting, but still entangled across vast scales. Some approaches interpret the thermal nature of the CMB as a reduced density matrix, obtained by tracing over inaccessible degrees of freedom. In this view, temperature emerges from entanglement, not heat. This idea connects cosmic temperature to decoherence, quantum information loss, horizon physics. The holographic principle suggests information in a volume is encoded on its boundary. If spacetime is holographic, temperature becomes a boundary phenomenon linked to horizon entropy. In cosmology, the observable universe has a horizon. Horizons possess temperature. This raises a non-trivial possibility. The sky's temperature may not be purely volumetric, but partially holographic in origin. This idea remains speculative, but mathematically consistent in certain frameworks. Photons are not the only cosmic relic. Neutrinos decoupled earlier. They also form a background, with a predicted temperature of about 1.95 K. This shows cosmic temperature is not unique. Multiple thermal relics coexist. Each thermal relic reflects interaction strength, decoupling epoch, degrees of freedom. Thus, the sky's temperature is part of a thermal hierarchy, not a single phenomenon. At sufficiently late times, photon density becomes extremely low. Interaction times exceed cosmic age. At that point, temperature remains mathematically definable, but physically unmeasurable. This distinction is central in modern statistical mechanics. Roger Penrose emphasized a paradox. The early universe had high thermal entropy, but extremely low gravitational entropy. This asymmetry underlies structure formation, the arrow of time, the existence of stars in life. The uniform sky temperature is evidence of thermal equilibrium, gravitational disequilibrium, a rare and unexplained combination. In quantum field theory, temperature is introduced through imaginary time. The partition function of a quantum system at temperature T is written as a Euclidean path integral with periodicity tau similar to tau plus beta, where beta equals 1 over kBt. This formalism implies something subtle. Temperature corresponds to a compactification of time. In this sense, the sky's temperature is equivalent to saying the quantum fields describing radiation admit a Euclidean time periodicity. That periodicity survives cosmic expansion. Thus, temperature is not an attribute of photons alone, but of the quantum structure of spacetime evolution. In algebraic quantum field theory, thermal states are characterized by the Kubo-Martin-Schwinger condition. A state is thermal if its correlation functions satisfy angled A of T B of 0 angled equals angled B of 0 A of T plus I beta angled. The cosmic microwave background satisfies KMS conditions to extremely high precision. This implies the sky's temperature is encoded in correlation functions, not merely in energy spectra. Temperature here becomes a property of quantum correlations, not classical averages. As the universe expands, physical scales change. This can be interpreted as a renormalization group, RG flow, in cosmological time. Under RG flow, high energy modes decouple. Effective temperatures rescale. Degrees of freedom change. The scaling law, T proportional to 1 over A, mirrors RG behavior. This analogy suggests cosmic cooling is a geometric renormalization process. This viewpoint is explored in effective field theory approaches to cosmology. At the microscopic level, most physical laws are time reversal invariant. Yet temperature is not. Thermal states break time reversal symmetry statistically and introduce irreversibility. The existence of a sky temperature therefore signals a global breaking of time reversal symmetry, rooted in cosmological initial conditions. This is not dynamical symmetry breaking, but boundary condition symmetry breaking.
The cosmic radiation field is not evolving toward equilibrium. It is equilibrium, but frozen. This places it in a rare category, a stationary non-equilibrium relic. Modern non-equilibrium statistical mechanics studies such systems under aging phenomena, frozen distributions, memory-preserving dynamics. The sky's temperature is an extreme case of infinite relaxation time. Define entropy as S equals minus Kb sum Pi log Pi. The Planck distribution maximizes entropy subject to energy constraints. Thus, the sky's temperature represents maximal ignorance given the total radiation energy. From an information perspective, the universe chose the least informative radiation state compatible with its expansion. This interpretation aligns with Jane's principle of maximum entropy. Temperature is only meaningful if it can be measured. The CMB temperature is inferred from antenna temperature, brightness temperature, and spectral radiance. Each definition converges to the same value. This convergence implies the sky's temperature is not a convention, it is operationally robust. Even in the absence of matter, temperature remains measurable. Consider the limit n gamma towards 0. In this regime, temperature remains mathematically definable. Energy density vanishes. Measurement becomes impossible. This exposes a conceptual boundary. Temperature can exist without physical instantiation. This challenges classical interpretations of thermodynamics. Radiation contributes to the stress-energy tensor. T mu mu of gamma equals 1/3 rho gamma g mu nu. Thus, the sky's temperature curves spacetime, alters expansion dynamics, influences early universe evolution. Temperature here is not passive, it is gravitationally active.
Einstein's equations require initial conditions. The cosmic temperature is part of that data. It is not derived, it is specified. This aligns with Wheeler-DeWitt cosmology, path integral boundary conditions, no boundary proposals. The temperature of the sky is therefore a cosmological input, not a consequence. In finite temperature quantum field theory, the emergence of temperature is equivalent to imaginary time periodicity. This is not an analogy, it is an identity. A quantum field at temperature T satisfies phi of tau equals phi of tau plus beta, beta equals 1 over kBt. This means the time dimension becomes compact. Now consider cosmology. The early universe can be described by a Euclideanized space-time segment, especially in approaches such as Hartley-Hawking no-boundary proposal, Vilenkin Tunnelin wave function, Euclidean quantum gravity. In these formulations, the initial thermal nature of radiation emerges naturally from Euclidean space-time geometry, not from microscopic collisions. Thus, the sky's temperature may originate from the topology of spacetime itself at early times. This is not metaphorical, it is a mathematically precise statement in path integral cosmology. A horizon is not merely a geometric boundary, it is a thermodynamic object. Black hole horizons have entropy S equals kBa over 4Lp squared. Temperature T equals h bar kappa over 2 pi kBc. Cosmological horizons obey analogous relations. In an accelerating universe, a de Sitter horizon forms. That horizon possesses a temperature. This leads to a disturbing possibility. The sky's temperature may be partially horizon-generated, not purely relic radiation. At late times, when relic photons redshift away, horizon temperature may dominate. Space itself radiates thermally. Temperature becomes a geometric inevitability, not a historical accident. In quantum field theory, the vacuum is not empty. It possesses zero-point fluctuations, vacuum expectation values, and stress energy contributions. However, vacuum energy does not define a temperature in the usual sense. Yet, when horizons are present, vacuum states become thermal, pure states become mixed, temperature emerges from tracing out inaccessible modes. This is central to Hawking radiation, Unruh effect, and Gibbons Hawking temperature. The cosmic sky temperature exists alongside these effects, raising a deeper question.
Is the observed temperature a property of matter fields or of inaccessible degrees of freedom? Temperature requires coarse graining. Exact microstates do not have temperature. In cosmology, we coarse grain over unobservable regions, over superhorizon modes, over inaccessible quantum phases. The sky's temperature emerges only after this coarse graining. Without it, the universe is in a pure quantum state. Temperature is undefined. Thus, cosmic temperature is observer-dependent in an information-theoretical sense, but invariant in practice.
Even though the CMB temperature is measured as 2.725 K, this value is subject to cosmic variance. We observe one universe, one realization of random fluctuations. The temperature is not ensemble averaged over universes, but conditioned on our cosmic history. This introduces a subtle statistical limitation. Temperature is precise, but not fundamental in the Platonic sense. This distinction is crucial in modern cosmology. In principle, any weakly interacting field present in the early universe acquires a temperature. This includes neutrinos, gravitational waves, and hypothetical dark sector fields. Each relic temperature reflects coupling strength, freeze-out epoch, and expansion history. Thus, the sky's temperature is one member of a thermal spectrum of the universe. A stochastic gravitational wave background can also be assigned an effective temperature. Unlike photons, gravitational waves interact extremely weakly. Their temperature is almost purely kinematic. This implies temperature is not tied to dissipation, it is tied to statistical structure. Classically, temperature requires matter. Heat requires contact, cold requires emptiness. Cosmic temperature violates all three intuitions. It exists because quantum fields exist everywhere. Expansion preserves distributions, geometry enforces structure. The sky has a temperature because classical thermodynamics is incomplete. At the most fundamental level, the universe may be described by a wave functional, with no classical spacetime, no particles, no temperature. Temperature appears only after decoherence, emergence of spacetime, classicalization of fields. Thus, the sky's temperature is an emergent phenomenon, not fundamental. In cosmology, there is no external heat bath. The universe as a whole must be treated, if at all, as a microcanonical system. Fixed total energy, no exchange with an exterior, no global thermal reservoir. Yet we routinely use canonical temperature to describe cosmic radiation. This is not trivial. The justification comes from the fact that subsystems of large isolated systems appear thermal when traced over the rest. Thus, the sky's temperature is a reduced description, derived from ignoring most degrees of freedom, valid only under coarse graining. This aligns with the idea that temperature is not a property of the universe, but of our partial access to it. A striking cosmological invariant is SA cubed equals constant, where S is entropy density. This means total entropy in a co-moving volume is conserved, despite expansion, despite cooling. The cosmic microwave background obeys this exactly. Thus, temperature decreases not because entropy is lost, but because entropy is diluted geometrically. This makes cosmic cooling fundamentally different from laboratory cooling. Standard statistical mechanics assumes ergodicity. Systems explore all accessible microstates. The universe is not ergodic. It does not revisit past states, sample phase space uniformly, relax dynamically. Yet temperature remains well-defined. This indicates cosmic temperature does not require ergodicity. This challenges one of the core assumptions of equilibrium statistical mechanics. Temperature is asymmetric in time. A thermal state has a well-defined past, no preferred future. The existence of a sky temperature therefore implies a thermodynamic arrow of time, embedded into space-time structure. This arrow is not emergent from dynamics, it is imposed by initial conditions. Thus, temperature encodes cosmological time asymmetry. In quantum information theory, one defines entanglement temperature, a parameter describing reduced density matrices without actual heat exchange. The CMB temperature may be partially entanglement-based. If so, the universe may be globally pure, locally thermal, with temperature arising from tracing over inaccessible modes. This interpretation dissolves the classical notion of hot and cooled. Radiation pressure contributes to cosmic dynamics. P equals 1/3 rho. Thus, temperature influences expansion, expansion influences temperature. This feedback loop is weak today, but dominant early on. Temperature is therefore not passive. It actively shaped space-time geometry. Empty space has fields, has fluctuations, has structure, has memory. Temperature quantifies one aspect of that memory. The sky's temperature is a measure of past interactions, lost correlations, frozen histories. Eventually, photon wavelengths exceed the observable universe. Radiation becomes operationally undetectable, yet temperature remains mathematically definable. This creates a divergence between physical observability and theoretical existence. Temperature survives as a formal concept beyond measurement. The so-called heat death of the universe is often misunderstood. It does not mean no temperature, no energy, no structure. It means no usable gradients. The sky's temperature is part of that asymptotic state, not zero, but uniform. The existence of a well-defined sky temperature requires quantum fields, expanding spacetime, specific initial conditions, weak interactions, horizon structure.
Even at the smallest scales, the sky's temperature reflects the underlying quantum microstructure of spacetime. Fluctuations in the CMB correspond to quantum density perturbations stretched by inflation. These tiny anisotropies encode both energy and information about the early universe. Planck and WMAP data show that the temperature varies only by 1 part in 100,000, revealing remarkable uniformity. Temperature, therefore, is not just an energy measure, it's a fossil imprint of the universe's earliest quantum states. Decoherence provides a bridge between quantum states and classical observables. In the early universe, photons interacted strongly with matter, maintaining a coherent thermal state. As photons decoupled, they carried away classical information about the early universe while still preserving statistical properties. Thus, the sky's temperature is the classical manifestation of a quantum history. The uniformity of the sky's temperature is intimately tied to temporal asymmetry. A thermal distribution requires a low entropy past, which allows for the highly ordered initial state of the universe. The observable universe's expansion ensures that temperature gradually decreases, marking a directional flow of time. Cosmic temperature, therefore, is both a thermodynamic measure and a temporal marker, linking energy, entropy, and causality. Photons are not the only relics carrying a temperature. Neutrinos decoupled earlier, producing a predicted cosmic neutrino background, 1.95 K. Hypothetical dark sector particles may also carry residual temperatures. Gravitational waves can have an effective temperature, defined statistically by their energy distribution. The sky's temperature is one part of a thermal hierarchy of the universe, reflecting both interaction strength and decoupling epoch. In a relativistic context, energy density and pressure satisfy ρ equals 3p, and temperature scales with the scale factor as T proportional to 1 over A of T. The energy momentum tensor T mu nu contributes to the Einstein field equations, linking temperature directly to cosmic dynamics. Thus, the sky's temperature is not passive, it actively influences the evolution of spacetime. Horizon physics adds further depth. Horizons, cosmological or black hole, introduce thermal behavior through entanglement across causally disconnected regions. The Gibbons-Hawking temperature demonstrates that observers in de Sitter space perceive a thermal bath even in vacuum. The CMB may therefore reflect both local relic radiation and horizon-induced thermal effects. Temperature becomes a hybrid property, partly emergent from matter, partly from space-time geometry. Modern approaches interpret cosmic temperature as information. Maximum entropy of radiation corresponds to maximum ignorance given constraints. The uniformity of the CMB encodes constraints on initial conditions. Tiny fluctuations are information carriers seeding large-scale structure. The sky's temperature is therefore simultaneously a thermodynamic variable and an informational measure. At the deepest level, quantum gravity frameworks such as loop quantum cosmology or string theory suggest that temperature emerges as a boundary condition of the universe's wave function. Euclidean path integrals imply that the early universe's thermal properties are encoded in the topology of spacetime. The observable CMB temperature is therefore both a relic and a signature of fundamental physics beyond current experimental reach. By studying the sky's temperature, we infer the state of the universe 380,000 years after the Big Bang. Tiny anisotropies reveal the inflationary epoch and primordial density fluctuations. Temperature measurements constrain cosmological parameters, particle content, and explanation history. The CMB temperature is simultaneously a thermodynamic variable, a historical record, and a probe of fundamental physics. As the universe expands, photon wavelengths stretch, reducing energy. Temperature drops according to T proportional to 1 over A. The universe will become increasingly cold, uniform, and dilute, approaching but never reaching absolute zero. This gradual cooling links cosmic thermodynamics to cosmological evolution, connecting initial conditions, dynamics, and statistical physics.
The sky's temperature is a record of the universe's history, from the early hot plasma to the decoupled photons we observe today. From initial quantum fluctuations to the large-scale structures they seeded. From isotropy to tiny anisotropies revealing density perturbations. Observational missions, COBE, WMAP, Planck, have shown that every photon carries a piece of this story, encoding both energy and information. The 2.725 K of the sky is more than a number. At cosmic scales, it measures expansion and energy density. At quantum scales, it reflects entanglement and decoherence. At informational scales, it represents a maximal entropy distribution constrained by the early universe. Temperature connects microphysics, macrophysics, and cosmology in a seamless chain. While not a fundamental constant like C or H bar, the CMB temperature is a practically universal reference. It defines a thermal background for all cosmic observations. It sets a baseline for particle relics, gravitational waves, and hypothetical dark sector fields. It provides a thermodynamic framework for understanding spacetime and matter together. The sky's temperature is a memory of the universe. It preserves the imprint of initial conditions. It encodes the physics of the early universe. It remains measurable billions of years later, bridging past and present. It is both ancient and enduring, a silent witness to cosmic evolution. The sky has a temperature because radiation, expansion, quantum mechanics, and space-time geometry are intertwined. It is a thermodynamic, informational, and historical quantity, continuously decreasing yet never disappearing. Measuring it is not just reading a number, it is listening to the universe itself, feeling the faint echo of creation. The sky's 2.725 K is a constant whisper of cosmic history, inviting observation, reflection, and endless curiosity.